All right. I wanted to talk about the last problem from Google Codejam Round 3, which I thought was pretty cool. It's an interactive problem where you have to play a game against the computer. And the game is you have some tree on n vertices, and every turn, whoever's turn it is, they get to pick a vertex and delete that vertex and any of its neighbors. And if you finish deleting the entire tree, then you win. And so the computer gets to go first, but we get to pick the tree. So the challenge is to pick a tree so that we can win every game, even though the computer gets to go first. And in the easy test case, we just need to find one tree with 30 vertices. And in the hard test case, we need to find 9 more trees with between 31 and 40 vertices, and still win every game. And I think we need to play out 50 games on each of these trees, to prove that we can win no matter what. And you have to win every time, right? So you have to find a tree that you're guaranteed to win. So that's the problem. And there's some pretty cool theory here. So this is an example of an impartial game, which means that it doesn't matter whose turn it is. You have the same set of legal moves for both players, which is you can pick a vertex and delete that vertex and any of its children. And so there's Sprague-Gundy theorem, which tells us how to solve games like that. And the way that you can solve them is any position in the game, you can assign a number called a number, a positive non-negative integer. And 0 means that the player whose turn it is will lose the game with perfect play. And non-zero means the player whose turn it is will win the game with perfect play. So how do we compute those numbers? The number is the MEX of the number of all of the positions that you could move to. MEX means minimum excluded. So the MEX of a list of numbers means the smallest natural number that isn't in the list. So if there's a bunch of numbers but there's no 0, then the MEX is 0. If there's a 0 but there's no 1, then the MEX is 1, right? And so on. It's the smallest element that isn't in the smallest number that isn't in the list. Okay, and then the last fact that we need from this theory is that if we say cut the tree in the middle and divide it into multiple trees, then the number of that forest, right, of those multiple trees, is just the XOR of the numbers of the individual trees. So that makes the computation a lot faster. So we can just, instead of looking at the whole thing, we can just look at the pieces that we split into. Okay, so I'm not going to prove any of that, but those are some cool facts from this game theory. And now let's see how to use it to solve the problem. So we can think of the problem as just find a tree with number 0, right? That means that the computer always starts. So we find a tree so that the starting player loses. And so we can just try a bunch of trees, but get to that, which trees, I'll get to that later. And if we can find one with number 0, then we can just use that tree to win the game. And we can compute the number of a tree relatively straightforwardly. Just try all possible moves. Literally just apply this definition. Right? Try all possible moves, compute the numbers, and take their max. And if we memorize that, that'll be reasonably fast. And also, we need to sort of reduce the trees so that we don't compute the same tree multiple times. So I'll get into that later as well. But in principle, this is straightforward. We can just apply this definition. And then once you have such a tree, it's very easy to win the game. So they make a move. We know that they move to a position where the number is not 0, because that's what it means for our starting position to have number 0. It means that in all of the successor positions, there was no 0. So 0 is the minimum excluded element. So they need to move to a number with a positive number. And now, because whatever they move to has a positive number, there's a move that takes us to number 0, right? Because the minimum excluded element was positive, so it wasn't 0. So 0 is in the list of successor positions. And so we just need to try all possible moves and figure out what numbers they result in, and then move to the one with 0. Right? So initially they're in a losing position. They move to a position that we can win from, so then we move them back to a losing position. Right? This is what it means to be in a losing position, is that every move takes you to a winning position for your opponent. And to be in a winning position means that there is a move that takes you to a losing position for your opponent. So every turn they're in a losing position until finally they're in the final losing position of the entire tree being deleted. So that's how we play out the game. So yeah, once you know this, like, these key facts from the theory, the sort of algorithm is not that complicated. The code is kind of long. I wrote like 350 lines to solve this problem. And also it runs pretty slow. I'll talk about that later. So let's try and talk about this in some intelligent fashion. Okay, so here is my solution to actually like play out the games. So these are the cool trees that I found, which I'll get to what that means later. This is like a tree with one vertex at the top, and then these 5 branches coming down of various lengths. So like this one is a branch of length 4, and then a branch of length 6, and then a path of length 6, and then a path of length 7, and then a path of length 7, which has 31 vertices, right, including the one at the top, and so on. So I'll get to how I found those later. But like supposing that you have them, you construct that tree. I guess maybe I'll show that. So this is like given these so we have like the lengths of the paths that we want to drop off of the central node. And so the total, size of the tree is like the central node plus the length of all these paths. And the path can be vertex 0. Right, so a tree, we're saying, is just a list of edges. Right, this is like the general form of a graph. It's like an adjacency matrix, right, for each vertex. What are its neighbors? That comment is wrong. Okay. Yeah, so the central vertex is vertex 0, and then we just drop all of the paths down, right? So the first node on the path is connected to 0, and vice versa, and then each node on the path is connected to the previous node on the path. So that's what make tree does. Okay, so then to actually play out the game, so first you write down our tree, and then we're going to play m games against them. And so we're going to keep track of which vertices have been deleted. Initially, nothing. So they get to take a turn in which they delete, some vertex and its neighbors. So we're just going to mark all the vertices that they said they deleted as deleted. And then you can check that in Nimber, which I'm calling Grundy here, is not 0. And then just try all possible moves. So for each possible move, if it results in a position with Nimber 0, then we're actually going to make that move. Yeah, okay. So we need to figure out like how many vertices we deleted, and also like which vertex. Right, we deleted a vertex and some of its neighbors, so the way I've written this here, we only get like which vertices we deleted, so we need to figure out which one was like the center. That's what this first thing is. And then print that out, and then like repeatedly do that. Right, so you just keep moving to the position with number 0. I guess the complicated part here is maybe this thing, which generates the list of possible moves. So this is like which vertices will be deleted after this move. Right, that's how we're sort of tracking a position in this game, is the vertices that have been deleted. So we can delete an undeleted vertex and then some subset of its neighbors. Right, these are like all the possible subsets. This doesn't really work in general. If a tree had like 30 neighbors, this would run way too slow because we would move through all like billion subsets. But fortunately, we get to pick the trees. So we can just pick, like in the graphs that in the trees we're going to be looking at, you only have at most 5 neighbors. It's only one vertex with 5 neighbors, so this is quite fast. So like move through all sets of neighbors, and those are each like one possible move. I guess we can also find the number of a position. So given like which vertices we've deleted, like figure out what trees result after you delete those vertices, and then just like XOR the numbers of all of those trees. So this is maybe the trickiest function, which is that. So one thing that's tricky here is we want to relabel the vertices so that, right, so like this might break the tree into multiple pieces, which is why we return a vector of trees. And we want each of those pieces to have vertices labeled like 0, 1, 2, 3. The reason for this is that we're going to memorize computing the Grundy numbers of various trees. Right, so if we've already seen a tree before, just like use the already computed value instead of computing a new value. Right, this is like memorization or dynamic programming. We really need this to run in time because there's like many possible sequences of moves to delete the tree. Right, you could just like delete the n vertices in any order, for example. That's like already n factorial ways to delete the tree. 30 factorial is a very big number, so we need memorization, and it's important that if we need to keep track of whether or not we've seen the same tree before, which is actually surprisingly tricky. Like this tree would be the same if you swapped, so the positions of 2 and 3, or if you labeled like this vertex like 4, 5, and 6. Right, it's like all the same tree, and so we need to make sure that we're not, figuring out the same tree like over and over again. And so in particular, when we're like breaking up these trees into pieces, we want each piece to be labeled from like 0 to n. We could actually be even smarter probably and like sort the vertices by like their degree or something to try and like just make sure we don't have too many like different names for the same tree. This is called like These are called like isomorphisms of a tree, like ways to relabel the vertices that don't actually change anything. So yeah, anyway, that's what I'm doing with this name thing, is like, imagine we have this tree. So this gives us 1, 2, 3, and 5, 6, 7. Right, like if we just returned these pieces as is, then we would end up computing the same thing twice, right? Because like these are both just paths of length 3. They're going to have the same number. So ideally, we would give them the same like identity, so that we don't repeat work. Yeah. So that's like the main difficulty of this function, is like labeling the pieces in a good way. And I actually didn't do like a super great job. Right, I just labeled them like so that their vertices are like 0 through n-1. You could be smarter and like, right, because like 1, 2, 3. Yeah. Okay. So what we're going to do is it's basically like traversing components of a graph. So if we come to a vertex that hasn't been deleted, start a new tree there. And so this is like the renaming map, and then just do a BFS through that tree. Don't go through deleted vertices. And when you're returning the new tree, like it's going to be in terms of the new names for each vertex, which are like smaller integers. So that will cause us to return like the same tree twice in this case instead of two separate trees. Yeah. So U is just going to be another adjacency list in this format, which is what we get when we do a BFS through our tree, starting at this vertex. And then the final answer is just like all of those different subcomponents of the tree, which we got from BFS. So yeah, this is like the main operation, right? Because when we make a move, we delete some vertices, and then we need to know sort of where we are after that, which is this like list of trees. Yeah, so let me talk about this main function, which is like actually computes the number of a tree. So if we've deleted everything, then the number is 0, right? There's no moves left. That's like our base case. If we've already computed the number, then just return that. And otherwise, we're going to keep track of the things of like which numbers we've seen in our successors. So generate a list of possible moves, which is just like go through all the vertices, and this is going to be a list of vertices to delete. So try deleting each possible vertex and each subset of its neighbors. And then, for each of those sets of vertices to remove, figure out like what position what trees are left after you remove those vertices. Recursively compute the numbers of each of those trees, XOR them together, and that's the number of like the position after that move. So mark down that we've seen that number, and increment, if this is supposed to be the smallest thing that we haven't seen, so keep track of that. And then the final number is whatever this smallest thing we haven't seen ends up being. I sort of assumed that it would be less than 100, which I cannot really prove to you why that is true. My guess is that with a tree of n vertices, like you need about n vertices to get to number n. Actually, yeah, you can probably prove that like pretty easily with induction. The point is like any move from n vertices moves you down to n minus 1 vertices. So if those n minus 1 can only get up to number n minus 1, then we can only go up to number n. So anyway, I could probably make this 50. I mean, I could definitely make this 50. That's what we just proved, and that would be fun. Anyway, so that's the core function that returns the number for a tree. Okay, so that's how you play at the moves. But this required like knowing what these trees were in advance. So how did I find those? So that's what this find function is for, which is just for each size between 30 and 40. We're just going to try all possible like lengths of 5 paths coming out of it. You might ask how I got to how I picked like this particular structure of tree. So initially I thought, I'll just do nodes with 2 paths coming out of it. Oh wait, that's actually just 1 path. And 1 path doesn't work because you can always just split it in half. Size pieces by deleting and see. Yeah, so I guess this is a simple consequence of this XOR rule. is if you have two equal size pieces left, then it's always a losing position because whatever you do in one piece, the opponent can just mirror in the other piece, or whatever number that piece has, like the XOR with itself, will always be 0. Is sort of the way to see that with numbers, but in that case, it's so simple that you can just see it directly. So that, yeah, paths can't work because of that. Like, you can always just cut it in the middle into two equal paths. So, okay, I was like, well, okay, fine. How about like 3 paths coming down from a central node? That seems like the next simplest thing. So that does actually work for like 30 and a few other cases. Like, as you can see, like this one is actually just 3, this one's just 3, 3, 3. But it doesn't work for some of these other cases, like 31 and 33 are particularly tricky. So anyway, just try 4 branches, and then try 5, and that happens to work. To save on search space, we can require that like the first branch is the smallest, and the second branch is bigger, and so on, right? Because if we just like permute the order, that doesn't change the number. That should be clear. So yeah, this just cuts down on how many trees we have to search. So like, just try looking through all of these trees. If we find one with number 0, then like write that down. And yeah, so that's how we found the trees. This takes like 8 minutes or so to find them all, which is too slow to do like during the submission, but we can just do it before we submit, right? And then just write down whatever we figured out in the code. That's what I did. And then, yeah, you can play out these games, starting on these trees, and win every time, like just following that strategy. And so I have a bunch of sort of print statements here to like, tell us how the game is going, basically. Yeah, so that's pretty much all there is to say about this problem. Which, I don't know, I think it's just like a cool setup, like cool use of interactivity, and like actually pretty algorithmically straightforward. Like if you happen to know this stuff about impartial games, which I don't know, it's a somewhat random thing to know, but it's also kind of a cool result. Like basically any game that has this particular property, like you can solve in this way. It's called a nimber, by the way, because like the first such game is called nim. Anyway, I won't get into that too much. But yeah, that's the problem.